Hello, dear learners, and welcome back to the Lesson BCE YouTube channel. Today, we are diving into one of the most fundamental and honestly coolest forces in the universe, magnetism. We're going to break down everything from magnetic poles to the invisible fields they create and how we can actually see them. Let's get right into it. But hey, before we start, if you enjoy learning about physics with us, make sure you hit that subscribe button and give this a like. It really helps us keep making these lessons, and you won't miss out on what's coming up next.
All right, first up, you know how a magnet can mysteriously push or pull on things without even touching them? Well, it all starts with something we call magnetic poles.
So every single magnet, doesn't matter if it's a huge one in a lab or the one holding a drawing on your fridge, has two special spots, a north pole and a south pole. These are the points where that magnetic push or pull is the absolute strongest.
And these poles have a really simple but super important rule. It's a lot like electric charges, actually. Opposites attract and likes repel. So if you bring a north pole near a south pole, they'll snap together. But try to push two north poles together, they'll fight you and push each other apart. Same goes for two south poles.
And this image shows that perfectly. Just look at the lines between the north and south poles on the left. See how they connect, flowing right from one to the other? That's attraction in action. Now, look at the two north poles on the right. The lines totally bend away from each other. They're pushing apart. You can literally see the repulsion happening.
Now here is a really wild fact about magnets. You can never, ever have just one pole by itself. They always come in a north-south pair. If you take a bar magnet and break it in half, you don't get a separate north piece and a separate south piece. Nope. You just get two new, smaller magnets, and each one has its own north and south pole. Scientists have looked for these single poles, called magnetic monopoles, but so far, they've never been found.
Okay, so magnets have poles that attract and repel, but how does that force actually reach across space? Well, that brings us to our next big idea, the magnetic field. The magnetic field is basically an invisible zone of influence all around a magnet. It's the region where the magnetic forces are at work. We use the symbol B to talk about it, and we measure how strong it is in a unit called the Tesla, or T for short. So how do we know this invisible field is even there? Well, we can make it visible. If you sprinkle tiny iron filings around a magnet, they don't just fall randomly. They actually line up and trace out the exact shape of the magnetic field. Each little piece of iron acts like a tiny compass needle. And speaking of compasses, this is the exact same reason a compass needle points north. It's lining itself up with the Earth's giant magnetic field. Those amazing patterns that the iron filings make, well, physicists have a name for them. We call them magnetic field lines, and they have some very specific rules they have to follow. Think of these lines as a map of the magnetic force. First, they always travel out of the North Pole and curve around into the South Pole. Then, inside the magnet, they complete the journey back to the north, forming continuous, closed loops. They never, ever cross each other. And here's the most important part. The closer the lines are packed together, the stronger the magnetic field is in that area. Okay, we've got the concepts down. Now let's switch gears a little and see how we can actually put a number on the strength of a magnetic field in a really common situation. So get this, it turns out you don't even need a traditional magnet to create a magnetic field. Anytime you have a moving electric charge, you get one. That means a simple wire with an electric current, which we call I, flowing through it, will generate its own magnetic field, and it forms these perfect circles all around the wire. And believe it or not, we can calculate the strength of that field with a pretty straightforward formula. B is our magnetic field strength, I is the electric current in the wire, and R is just how far away from the wire you are. That other symbol, μ0, is a constant of nature. It basically just tells us how easily a magnetic field can set up in empty space. The main thing to notice is that a bigger current, or I, makes a stronger field, and moving farther away, a bigger R makes the field weaker. Makes sense, right? Theory is great, but let's make this feel a bit more real. We're going to take that formula and apply it to an actual problem. So here's our setup. We have a straight wire, and there's a current of 5 amps flowing through it. Our mission is to figure out the magnetic field strength B at a distance of 0.02 meters. That's about 2 centimeters away from the wire. Okay, let's walk through it. First, we write down our formula. Easy enough. Step 2, we plug in all the numbers we know. The value for our constant, μ0, is 4 pi times 10 to the minus 7, our current, I, is 5, and our distance, r, is 0.02. Now for the fun part, simplifying. Notice how we have 4 pi on top and 2 pi on the bottom? They simplify really nicely. That leaves us with a much cleaner expression in step 3, which leads us straight to the answer.
And the result is 5 times 10 to the negative 5 Tesla. And that's it. That is the actual strength of the magnetic field at that specific point. It might seem like a small number, but it's a real, measurable force created just by that flowing electricity.
All right, time for a quick concept check to make sure one of our key ideas really stuck. If you're looking at a diagram of a magnetic field, and you see the field lines are all bunched up really close together in one area, what does that tell you?
You got it. It means the magnetic field in that region is stronger. The density of the lines is a direct visual clue to the field's strength. That's a huge takeaway.
So, let's just quickly recap the 3 big ideas we covered today. First, we learned about magnetic poles, that every magnet has a north and a south, and they control attraction and repulsion. Second, magnetic fields, that invisible force field that surrounds a magnet, which we measure in Teslas. And third, magnetic field lines, the tool we use to visualize the field's direction and strength.
And that's our deep dive into the fundamentals of magnetism. Thank you so much for joining and learning with us here at Lesson BCE.
We have a lot more exciting physics lessons coming your way very soon. So if you found this helpful, please don't forget to subscribe and hit that like button. We'll see you in the next one.